Somewhere near the equator, there's an island so ordinary it could be anywhere, until you realize two identical clocks that can't agree on what time it is. They started perfectly synchronized, but after 1 month, one of them was ahead by 36 nanoseconds. 36 nanoseconds. A fraction so small it's meaningless to human perception. But to physics, it's proof that time itself can bend. The island didn't move. Time did. The lead scientists stared at the data for 3 days. Rechecked the instruments. Flawless. Recalibrated the sensors. Perfect. The clocks hadn't malfunctioned. They'd simply disagreed on what a second means. Imagine standing there. Heat pressing down. Air so thick it feels like the planet itself is breathing. Palm trees lean toward the horizon. Waves strike the shore in rhythm like an ancient metronome. Everything looks normal, calm, harmless. Yet your heartbeat, your breathing, even the rhythm of your thoughts are ticking a few nanoseconds faster than someone standing at the poles. You'd never feel it, but the universe is keeping score. This wasn't a desolate, alien moon. It was a lush, quiet place where the only sound was the rustle of palms. Yet beneath that tranquility, the fundamental equation of the cosmos was being subtly, relentlessly warped. The clocks told two different versions of the truth. One of them experienced more time than the other, on the same planet, breathing the same air, spinning through the same day. Something about this island was stealing seconds and giving them back wrong. The answer was hiding in plain sight, in the one force we stop noticing the moment we're born. If your clock ran slower than everyone else's, just by a fraction you'd never feel, would you want to know? You felt it every second of your life, but never the way it's actually working. It's not pulling you down. It's bending time itself, and Einstein spent a decade proving it. He couldn't see it, but he could feel the contradiction. If gravity bends light, could it also bend the pace of time? Picture yourself sealed in an elevator in deep space. No stars, no up, no down. Suddenly, the floor presses against your feet. You drop a ball, it falls. But here's the question Einstein couldn't answer. Are you standing on Earth, feeling gravity pull you down, or accelerating upward through empty space? There's no way to tell. No experiment that could prove the difference. And if gravity and acceleration are indistinguishable, then gravity must be bending space-time itself. Now, stand on Mount Everest. You're 8,849 meters above sea level, and gravity's grip on you is slightly weaker. Wind tears at your face. Every breath is thinner. Your heartbeat races from a climb, and your clock is ticking faster than someone standing at sea level. Not by much. A climber who spent a year up here ages 15 microseconds more than someone below. 15 microseconds older. A difference you'd never feel, but one the universe tracks with mathematical precision. In 1959, two physicists proved it in a Harvard building. One atomic clock on the roof, one in the basement, 22 meters apart. After 1 day, the higher clock was ahead by 4.9 nanoseconds. 4 floors. 4 nanoseconds. Einstein was right. Gravity steals time. The stronger the gravity, the slower the clock. But on our island, Einstein's perfect math met a paradox. Its low altitude meant gravity should have dragged time down, yet something else was pulling it sideways. While general relativity explains gravity's drag, it couldn't explain this second thief, the one hiding in Earth's relentless speed. Einstein proved gravity bends time, but he missed the second thief, and it's right beneath your feet. Picture the Earth from space, a perfect blue sphere spinning through the dark. What looks calm from afar is actually violent motion. At the equator, the ground beneath your feet is hurtling eastward at 1,670 kilometers per hour. Near the poles, it barely moves at all. You don't feel that motion, but time does. Einstein's other theory, special relativity, says the faster you move, the slower your clock runs. Speed stretches time. Gravity crushes it. And on Earth, both forces are at war. At the equator, you're 21 kilometers farther from Earth's center than you are at the poles. Gravity weakens. Time should tick faster. But here's the catch. You're also moving at 1,670 kilometers per hour, dragged along by the planet's rotation. And motion slows time down. Two forces, opposite effects, both acting on the same second. They nearly cancel each other out. Nearly. That tiny leftover, those 36 nanoseconds our island clocks measured. The residue of a war between speed and gravity. So which force wins? Gravity slowing time, or velocity stretching it? Pause. Make your guess. The answer depends on where you stand. At the poles, gravity dominates. Time runs slower. At the equator, velocity fights back. Time runs a hair faster. But across the sea-level Earth, The balance is so perfect that the difference is almost invisible. That means right now, as you watch this, your time is unique. Someone at the equator lives through about 0.16 milliseconds more per year than someone at the poles. Over 80 years. Roughly 13 milliseconds. That's 1/60th of a single heartbeat. Not enough to notice, but enough that GPS, aviation, and every satellite in orbit must constantly correct for it. The Earth spins, time warps, and the difference is measurable. But here's the problem. If time runs differently everywhere on Earth, how do we ever agree on what time actually is? The question wasn't just theoretical anymore. If every place on Earth experiences time differently, someone needed to measure it, clock by clock, flight by flight. In 1971, two physicists at the U.S. Naval Observatory decided to try. They bought plane tickets, 4 atomic clocks, each one so precise it wouldn't lose a second in 3 million years. 2 flights, one east, one west. For 2 days, those clocks flew through time zones, turbulence, and Einstein's equations. When they landed, the scientists compared them to identical clocks that had stayed on the ground. The result? Time had shifted. The eastbound clock had lost 59 nanoseconds. The westbound clock had gained 273. Hundreds of nanoseconds. Exactly as Einstein predicted. Gravity and velocity were no longer abstract concepts. They were facts written in metal and oscillating atoms. They'd proven Einstein right. Time could be measured, tracked, bent by gravity and speed. But that created a problem no one anticipated. Because if time runs differently at every altitude and velocity, how do you build a navigation system that depends on perfect synchronization across dozens of satellites, each one moving at different speeds and heights? In the 1970s, the U.S. military started launching GPS satellites. Each one carried atomic clocks, and immediately, those clocks started drifting. Not because they were broken, but because relativity was pulling them in opposite directions. Gravity at altitude made them tick faster. Velocity in orbit made them tick slower. Combined effect? Each satellite gained 38 microseconds per day compared to clocks on Earth. 38 microseconds doesn't sound like much, but light travels 300 meters per microsecond, which means after one day, a GPS satellite's clock would be off by 11 kilometers. Your phone would place you blocks away from where you actually stand. Aircraft navigation would drift. The entire system would unravel within hours. So engineers programmed every GPS satellite to slow its clock artificially, ticking at 10.2299999543 MHz instead of a perfect 10.23 MHz. A permanent correction built into hardware, accounting for gravity and velocity every single second. Your phone recalculates this offset 4 times per second, just to keep your reality aligned with Einstein's. Today, we can measure time differences across the planet, down to the nanosecond. We know exactly how much faster your clock ticks at the equator, how much slower it runs at the poles. But that precision revealed something unsettling. If time runs differently everywhere, then when you say right now, whose now are you talking about? Picture 2 friends on a video call. One is in Quito, Ecuador, 2,850 meters above sea level. The other is in Amsterdam, barely above the ocean. They decide to count down together. 3, 2, 1, 0. Both hit 0 on their screens. But physics asks a question that no clock can answer. Whose 0 actually happened first? This is the relativity of simultaneity. There is no universal now. 2 events that seem simultaneous to one observer may occur at different times for another. Your location, your speed, even the altitude you occupy shapes your personal experience of the present. Astronauts aboard the International Space Station live this truth daily. Orbiting at 28,000 kilometers per hour, their clocks lag slightly behind ours, by about 0.007 seconds over 6 months. Scott Kelly's year in space made him younger than his twin on Earth. Not by choice, but by physics. He literally lived into the future. Back on Earth, this affects even everyday life subtly. Your video call, your shared laughter, your synchronized countdown. Each participant's now is slightly displaced in time. 2 people can experience the same second differently, and it's completely imperceptible until you measure it. Think about the person you talk to most. Are you ever truly in the same moment? Even across the globe, your hello is drifting through someone else's past or future. Every conversation, every shared experience is slightly time-shifted, an intimate paradox you live without noticing. This isn't just abstract philosophy. It's physics affecting perception. Your now is woven from motion, gravity, and velocity, unique to you. And it points to something profound. Wherever you're standing, you're not just choosing a place, you're choosing a win. Somewhere on that island, two people may share a meal, yet experience different slices of reality. And that is where the paradox of now becomes impossible to ignore. You're standing on that island near the equator. The sun climbs slowly. Waves whisper along the shore. Those two atomic clocks began perfectly synchronized, measuring the same seconds, ticking through the same reality. They ended 36 nanoseconds apart. Not because one failed, not because the measurements were wrong, but because time itself refused to agree on what a second means. Your heartbeat echoes through the stillness. Somewhere in the Andes, that same heartbeat would last a fraction longer. At sea level in Amsterdam, it would finish slightly sooner. 3 people, 3 heartbeats, all happening now, but none truly simultaneous. Every step you take on this island moves you through space, but it also moves you through time, nudging you into a slightly different version of now than the person standing 10 meters away. You can't escape it. Gravity bends your seconds. Velocity stretches them. The Earth spins you through a geometry of time that shifts with every breath. And here's what the island reveals. This isn't a flaw in the universe. It's how the universe works. The clocks aren't broken. They're honest. Each one measures its own truth. And both truths are correct. Every location on Earth is a choice. Not just where you are, but when you are. The altitude you occupy, the speed you move, the seconds you experience, all uniquely yours. Physics isn't distant. It's woven into every moment you live. The island, the clocks, the 36 nanoseconds, they're invitations to see reality as it actually is, layered, relative, infinitely personal. So when you check the time right now, are you checking yours or someone else's?